In this video, we're going to introduce Sturm-Liouville problems from Constanda's Solution Techniques for Elementary Partial Differential Equations, second edition. It's this book right here. And I think there's a new edition out right now. It's actually a very well-written book. I really love this book. We're going to talk about just some necessary background to define Sturm-Liouville problems. Then we'll discuss the definition of a Sturm-Liouville problem and show some specific examples of Sturm-Liouville problems, and we'll discuss eigenvalues and eigenfunctions. Now, if you've already seen these problems before, you can skip this video and go on to the next video where we'll actually be solving some Sturm-Liouville problems. But this is the necessary background to really understand what it is we're doing and why we're doing it. Now, before we get started, I just want to tell you what these are. These are a class of problems involving second order ODEs So we're not actually solving any partial differential equations yet. But these eigenfunctions and eigenvalues are very important when we're solving partial differential equations later with a couple of other methods. So this is a precursor. It's getting us ready to study a couple of other methods. Those methods include separation of variables and the eigenfunction expansion method, which are discussed in chapters 5 and 7 of this textbook. So let's say Sturm-Liouville problems are problems that will allow us to solve or will allow us to apply the methods of separation of variables and the eigenfunction expansion method. And those are very important in solving partial differential equations. And those partial differential equations are very important in applications, especially physics. You see a lot of partial differential equations in physics. So that's what we're about to do is solve these second order ODEs. But in order to get there, we need to talk about a couple of different definitions and functions. Oops, I said functions, I just meant definitions. Sorry about that. Okay, so let's start with our first definition. We want to let chi be a space of functions defined on an interval I. And whenever we say I, when we discuss Sturm-Liouville problems, that could be an open interval, it could be a closed interval, it can go from negative infinity to infinity, it can go from a constant to infinity or a negative infinity to a constant. It's just some interval on the real line. And this is the Greek letter chi. Here's our definition, a linear differential operator. L acting on that space of functions chi is called symmetric if the following is true. Symmetric on that space if the integral over I of one function of x times that linear operator applied to a second function minus that second function times the linear operator applied to the first function is equal to 0 for any functions f1 and f2 in that space of functions, chi. Now, if you are following along, this particular video is going to be very much by the book. I'm going to follow Dr. Constanda's book very closely. So if you want to, you can follow along in the book as well. But hopefully I'll add a little insight and some little reminders that will help you and remember some important prerequisites from other classes, for example. Okay, so this operator L is symmetric if this is true. And we're talking about a linear differential operator L. Now remember what an operator is. Basically, it acts on a function, and typically an operator will yield another function. So we have a differentiation operator, which is just the first derivative. That's a linear operator. An antiderivative is an operator. If you take the antiderivative of a function, you get a new function. And here we're saying that we've got a linear differential operator L. So just recall that this is true. We say that an operator L is linear. If you take that operator and you apply it to some linear combination of functions. I know I'm using linear in two ways, but we're saying we're taking this operator and we're applying it to a constant times f plus a constant times g. For some constants, a or alpha and beta, and those could be real numbers, they could be complex numbers. If this is equal to this, so you can factor out the constant and apply the operator to f, and then add what you get when you factor out the constant and apply the operator to g. You say that an operator is linear if it behaves like this. For some class or space of functions, f and g. So here's an example of a linear operator. Sometimes we'll call this just d for the differentiation operator, or we'll write d dx. Now remember that that doesn't really mean much without a function to the right of it. I need to take the derivative of something. But if I take this differentiation operator and I apply it to alpha f plus beta times g, you know from calculus that that's just going to be alpha f prime plus beta g prime. So that's the operator applied to f times alpha plus the operator applied to g times beta. And that's going to be true for all the differentiable functions f and g and real constants alpha and beta. And it turns out to also be true if those constants are complex. So this is a linear operator. Oops, there we go. And that's exactly what we're talking about. Okay, so we know that that's true. Now, let's go back up here. So we said, let chi be a space of functions defined on an interval I, a linear differential operator. That means an operator that is comprised of constants times differential operators. So this is just the first derivative operator, but I could have just as easily used the second derivative operator here. We could call that d squared, or we could write it that way in Leibniz notation. That just means take the second derivative, take the derivative twice. This is also a linear operator. And it turns out if I take this and I multiply it by a constant, like say 3 times the second derivative operator, it still works. I could distribute that 3 through everything and then regroup, and I would see that that's a linear operator. So whenever we talk about a linear differential operator, the linear differential operator is going to look something like this. Let's say it's nth order. An nth order linear differential operator. In that case, L would be, let's just say some constant a sub n times the nth derivative operator plus some constant a sub n minus 1 times the n minus 1th derivative operator plus some other constant a sub n minus 2 times the n minus 2nd derivative operator. And you would keep going until eventually you get a constant times the first derivative operator plus just a constant. If you take that and you apply that to a function y, all you're saying is do this to y. So it's like it distributes. So we would end up with that constant times the nth derivative of y with respect to x plus the next constant times the n minus 1th derivative of y with respect to x plus another constant times the n minus 2nd derivative of y with respect to x. And you just keep going until eventually you end up with dy dx times a constant plus a constant times y. So that is a linear operator. And I'm not going to show you here, but you can check for yourself that if this wasn't just y, but if it was, let's say, L applied to alpha y1 plus beta y2, it turns out that because of the form of this, if you were to apply that operator to this linear combination of functions y1 and y2, where alpha and beta are scalars, you would get alpha times the linear operator applied to the first function plus beta times the linear operator applied to the second function. Now, this is something that is not in the first page or the first chapter of that book of Dr. Constanda's partial differential equations book, that particular section on the Sturm-Liouville problems, but it's an important fact that you need to remember in order to understand this definition. So we've got a space of functions defined on an interval and a linear differential operator L. So it's an operator that kind of looks like this and it behaves like this. We call that linear operator L acting on the space of functions. I think I said X, I meant chi. We call that symmetric on chi if this is true. So you take F1 and you apply L to F2, and then you subtract F2 and you apply L to F1, and then you integrate over the interval. If you get 0 every time for any F1 and F2 in that space of functions chi, then the operator itself, L, is called symmetric. So let's look at an example. This is an example straight from the book. This is example 3.2. So chi is going to be a set of functions, and these functions are twice continuously differentiable. That means you can take the first and second derivative and both of them are continuous. Not for all real numbers. We just want them to be twice continuously differentiable on the interval from 0 to 1. And we want f of 0 and f of 1 to both be equal to 0. That's chi, okay? Now, if L is the second derivative operator, so we can write it like this. In some textbooks, I've seen it written like that. We can show that this operator L is symmetric on chi. Okay, so in order to do that, let's let F1 and F2 be members of chi. Remember what that means. These functions are in this set. That just means they're twice continuously differentiable functions, and f of 0 and f of 1 for each of those functions is equal to 0. Okay, then let's look at the integral over I, which is the interval from 0 to 1, of f1 times L applied to f2 minus f2 times L applied to f1. Now remember what f or L was. L is the second derivative operator. I'm going to switch from Leibniz notation to prime notation. So I have f1 times f sub 2 double prime. I'm going to write this as a difference of two integrals minus the integral from 0 to 1 of f sub 2 times f sub 1 double prime. Okay, now it's very easy to show using integration by parts that this will ultimately be 0. And that's what we're trying to show. Remember the definition of a symmetric operator is that for all f1, f2 in this space of functions, we get 0 when we do this. So that's what we're trying to do. We're trying to show that this will be 0 all the time, as long as f1 and f2 are twice continuously differentiable and f sub 1 of 0 and f sub 1 of 1 are equal to 0, and f sub 2 of 0 and f sub 2 of 1 are both equal to 0. So all of that is baked into that little sign right there that says that these two functions are in that space. Okay. Now, if we just go back to calculus 2 and we do a little integration by parts, we can show that this is going to be 0. It's actually very simple. Now, remember with integration by parts, dv has to be something that you can take the antiderivative of. So we're going to let u be f1, and we'll let dv be f sub 2 double prime. And that makes sense because I know that the antiderivative of f sub 2 double prime is going to be f sub 2 prime. We're undoing differentiation by anti-differentiating. So that's just going to reduce the derivative by 1. Du is just the derivative of this function times dx. Now, when we do the integration by parts, we get uv minus the integral of v du. So you have f1 times f sub 2 prime. Now remember that will be evaluated at 0 and 1, and then we subtract using the fundamental theorem of calculus. And then we'll have minus the integral of v times du. So it's minus the integral from 0 to 1 of f1 prime, f2 prime, dx. Minus, okay, over here we're going to do the same thing. It's very simple. U is equal to f2, du is equal to f sub 2 prime times dx. Again, we're taking that one to be u and dv to be f sub 1 double prime, because in order to undo differentiate, or in order to get v, we need to anti-differentiate. It's easiest to anti-differentiate when you're already starting with a derivative of something. So we'll take the antiderivative of the second derivative and we get the first derivative. And then by integration by parts, we're going to get u times v, evaluated from 0 to 1, minus the integral of v du. Now we're subtracting this, this difference here. So when I distribute this negative to that negative, I get a plus sign there. Negative times a negative is a positive. And you see right away that this term and this term reduce. And now you've got this evaluated at 0 and 1 and this evaluated at 0 and 1, and you subtract. And I think it's pretty obvious, but let's write it down. So we're going to have that minus that minus this minus the same expression evaluated at 0. This is x equals 0 now. Now remember the definition of this space. We're talking about sets of functions, or a set of functions that include twice differentiable functions, continuously differentiable. So these functions, second derivatives, they exist and they're continuous and they're nice on the interval from 0 to 1. And then at 0 and 1, the functions are both 0. So this is 0, and this is 0, and this is 0, and this is 0. So obviously the whole thing is 0. Now, since that is true for any functions f1 and f2 in that space chi, that means our linear operator, linear differential operator, which is the second derivative operator, is symmetric on chi. Now, one thing I want you to notice is that it's symmetric on chi. Maybe we should highlight that as well. And we're also talking about a particular interval. If we change the interval, things might change. If we change the space of functions, this may not, the condition of being symmetric may change. So we don't just talk about an operator being symmetric, we talk about an operator being symmetric on a space of functions, and that space of functions is associated with a particular interval. Yeah, this operator, the second derivative operator, is symmetric on this space of functions. But if I did not have this requirement that f of 0 and f of 1 are both equal to 0, I would get this result without this being 0 or this being 0, this being 0 or that being 0. There's no guarantee of any of this being 0. So yeah, that's what would happen if I changed that space of functions chi. So we don't want to do that. We want to leave that alone. In this example, we can show that this operator is symmetric, but it wouldn't necessarily be symmetric if this changed. So you have to take the conditions or the characteristics of the functions in that space of functions into account. All right, so that's our first definition, about symmetric operators on spaces of functions now. Here's another definition that's really important. This is the definition 3.4. It says, let sigma be a function defined on I with the property that sigma of x is greater than 0 for all x in I. Then two functions, f1 and f2, also defined in I, are defined on I. Are orthogonal with weight sigma on I if the following is true. If the integral over I of f1 times f2 times sigma, and those are all functions of x with respect to x, if that is equal to 0, then we say that those two functions are orthogonal to each other with weight sigma. Now, if sigma is just the function like y equals 1, it's 1 all the time, then we call f1 and f2 just orthogonal. And then a set of functions that are pairwise orthogonal that's called an orthogonal set. And you see lots of orthogonal sets. Turns out that the functions associated with these Sturm-Liouville problems form orthogonal sets. Okay, so I'm just going to go through a couple of examples, and I'm not going to do the integration because it's pretty simple. It's pretty straightforward. If you need help with that, don't hesitate to email me. I'd be happy to help you out. So this is example 3.5. If f1 of x is equal to 1 and f2 of x is equal to 9x minus 5, we say that these are orthogonal. With a weight of sigma of x equals x plus 1 on the interval from 0 to 1, since the following is true. Since the integral from 0 to 1 of 1 times 9x minus 5 times x plus 1, if we evaluate that integral, we get 0. And remember, that's what this says. It just says that if you take this function, and that weight function, you multiply them together and you integrate, you get 0. If that's true, then those functions are orthogonal with that weight. If we do the distribution, we get 9x squared plus 9x minus 5x is 4x plus 1, or it's not plus 1, sorry. 1 times negative 5 is going to be negative 5. And if we do the integration, gosh, I said I wasn't going to do it, but I want to do it. So let's do it. We get that. If you plug in 1, you get 3 plus 2 minus 5. Plug in 0, you get 0. Clearly that's 0. So you get 0 when you multiply these together and you integrate over the interval from 0 to 1. So that means these two functions are orthogonal with the weight of x plus 1. Now, if we wanted to, rather than thinking of 1 and 9x minus 5 as being orthogonal with this weight, we could just think of 9x minus 5 and x plus 1 as being two orthogonal functions. So you see that we can shift our perspective and see things in different ways. That's to be expected. But that is one definition of orthogonal functions with a particular weight, or one example of orthogonal functions with a particular weight. Here's another example. Got the integral from negative pi to pi of sine of 3x times cosine of 2x. Now there is a product to sum identity taught in calculus too, but also taught in trig, I'm sure, that says that if you've got sine of an angle times cosine of an angle, that function is the same as 1/2 of the sine of the sum of those angles plus the sine of the difference of those angles, provided those angles are both just a constant times your variable. So 3x plus 2x is 5x, 3x minus 2x is just x. If you do the integration from here, it turns out that you get 0. It's so simple that I'm just going to let you guys handle that one. But since that's true, we can say that sine of 3x and cosine of 2x are orthogonal to each other on the interval from negative pi to pi. Okay, so now we know about orthogonality and we know about symmetric operators. So that is enough for us to introduce the definition of an eigenvalue problem. This definition says, let L be a linear differential operator acting on a space of functions, and we'll call that space chi of functions. defined on the interval from A to B. Then an equation of the following form. L applied to F plus lambda times sigma times F equals 0 for x between A and B, where lambda is a real parameter. Sigma is a given function. And sigma of x is greater than 0 for all x in AB. An equation that looks like this is equation 3.1 in the text, is called an eigenvalue problem. Now our goal with this is to solve this differential equation for the unknown function f. The linear operator is going to be known. This weight sigma is going to be known. The lambdas are to be determined by us, and the function f is to be determined by us. Our goal is to find an infinite family of solutions to this differential equation. That infinite family of solutions is called a set of Eigen Functions. They're non-zero solutions to this differential equation. And the corresponding values of lambda are called the Eigenvalues. So let me write that down. It says the lambda, these are the numbers for which the differential equation has non-zero solutions in that space of functions chi that we're interested in. Those are called the eigenvalues. Of the differential equation. And the corresponding functions f to the corresponding solutions of the differential equation are called Eigen Functions. Again, big picture. I've got a differential equation. I've got a known operator over here. I've got a known function here. I've got an unknown f. I'm trying to find it. I've got an unknown lambda. I'm trying to find that as well. We're looking for the non-zero solutions f and the corresponding lambda that go with them. It turns out we're going to end up with infinitely many functions f. We're going to call those the Eigen Functions of the differential equation. And we're going to end up with corresponding number of, or corresponding eigenvalue for each of those Eigen Functions. We're going to have infinitely many of those eigenvalues as well. And we want to find both of those at the same time. So here is our next theorem. And this is why we had to talk about symmetry. If the operator L, that linear differential operator, of the eigenvalue problem 3.1 is symmetric. If that's true, if we've got a symmetric linear operator right here, then a few things are true. All the eigenvalues are real. That tells us something. They're not complex. Okay. What else do we know? We know that they form an infinite sequence. Lambda sub 1 is less than lambda sub 2, which is less than lambda sub 3. And it keeps going. We've got lambda sub n there. And as n goes to infinity, lambda sub n is going to go to infinity. And lastly, the eigenfunctions associated with distinct eigenvalues are orthogonal with a weight of sigma on the interval from A to B. So again, what does it mean to be orthogonal? That means if you take those two functions, you multiply them by sigma, and you evaluate that integral, you're going to get 0. So that's going to be true. There's an eigenfunction associated with each of these eigenvalues. So you've got infinitely many eigenvalues and a corresponding infinitely many eigenfunctions. And those functions are orthogonal from each other, which means this is true. All of the eigenvalues of the eigenvalue problem that we have right here are guaranteed to be real, and all of this is guaranteed to be true, provided that this operator L is symmetric. And again, what does it mean to be symmetric? It means that this is going to be 0 all the time. Okay, that's where we're at. Now, I am not an expert on physics or a lot of applications of these things. I would say I wish that I had taken more physics as an undergraduate, because I think it's really beautiful and really interesting, and there's a ton of overlap between what we learn in math and what we learn in physics. But I am not an expert in that in any way. But I will say that these eigenfunctions, these infinitely many eigenfunctions associated with infinitely many eigenvalues that solve this simple differential equation that we're talking about. It's just, and that's just a differential operator. So this is like it's an ODE. It's not even a partial differential equation. These functions are really important because it turns out that these are the building blocks of other functions. We're going to be able to come up with other functions by taking combinations of these eigenfunctions, and that's going to yield some other function. And that's what we're going to end up doing with the solutions of these Sturm-Liouville problems when we solve partial differential equations later. And those solutions are very important in physics. This is a class that if you are a physics major, or if you are interested in physics, it's really helpful to understand just the basics of how Sturm-Liouville problems work, and then how those contribute to solving, what did we say, problems using separation of variables and eigenfunction expansion. Because these functions are the building blocks for other functions. And that's very nice. It's very nice that sometimes the functions that we're interested in are poorly behaved individually, but then suddenly if you take a combination of them, they're not poorly behaved anymore. And that's very, very nice. So yeah, that's what we're trying to do. Now let's look at Sturm-Liouville problems. I've not quite gotten there yet, but we're almost there. So here's another definition. We want to let the interval from A to B be a finite interval. We want to let P, Q, and sigma be real valued functions. And we want to let kappa sub 1, kappa sub 2, kappa sub 3, and kappa sub 4 be real numbers. And we want that interval, these functions, and these real numbers to satisfy the following. So we're going to say, let this be true, and this be true, such that the following is true. First of all, P is continuously differentiable. So its derivative is continuous. On the interval from A to B. And we want P of X to be greater than 0 for all X in the interval from A to B. And we want Q and sigma. We want those to be continuous. On the interval from A to B. And we want sigma to be positive for all X in the interval from A to B. And finally, we want kappa 1 and kappa 2 to not both be 0. And we want kappa 3 and kappa 4 to not simultaneously be 0. Then a particular eigenvalue problem of a certain form is a Sturm-Liouville problem. So we've got P times F prime, that product prime, plus Q times F, plus lambda times sigma times F. Those are all functions of X. We set that equal to 0. So that is our differential equation. The unknown function here is F. We also don't know those parameters lambda. An eigenvalue problem of this type, where we're trying to find all the functions F that satisfy this equation that correspond to certain values of this parameter lambda, those eigenvalues. A problem that looks like this with the boundary conditions, which I will abbreviate BCs. Kappa 1 times F of A plus kappa 2 times F prime of A equals 0. And kappa 3 times F of B plus kappa 4 times F prime of B equals 0. A problem that looks like this, subject to these boundary conditions, is called a regular Sturm-Liouville problem. And that is the subject of chapter 3 in Dr. Constanda's book. And again, these are important. The solution methods we'll talk about later for partial differential equations. Eigenvalue or eigenfunction expansion and this method of separation of variables. They can all be solved as long as we know how to solve Sturm-Liouville ODEs. So that's the key to be able to solve those ODEs. And these are the particular ODEs that we're going to tend to be interested in. Now, there are a lot of conditions here. A couple of things I want to point out to you. P, Q, and sigma will be known. So this is just a differential equation. It's going to have a lambda in it, and it's going to have an F in it. You're going to be looking for F and try to find the values of lambda that would give you certain values for F. And of course, we're looking for non-zero solutions. So these are corresponding non-zero solutions of the differential equation. Of course, that's a homogeneous differential equation. Of course, we're going to get 0 if F is 0. That's not the solution we're looking for. We're definitely looking for a solution that's non-zero. And those are called eigenfunctions. Turns out that there are going to be infinitely many of them, subject or that correspond to infinitely many eigenvalues. And in particular, we're not just looking to solve this, we're looking to solve these for a particular P, Q, sigma, and for these particular boundary conditions. One thing that I want you to notice about the boundary conditions is the first boundary condition is dealing with the function and its derivative evaluated at x equals a, that left-hand endpoint of our interval. So this is not an initial value problem if you've had ordinary differential equations. In ordinary differential equations, we just have, if I had a second order differential equation like this, and that's what this would be after we expand that, right? Have a second derivative of f. I would typically have f evaluated at some initial value plus f prime and f prime evaluated at some initial value, and that would be it. The values of x or t, the independent variable that we were interested in, they would all be the same, and it would be an initial value problem. This is a little different. We're talking about a boundary value problem, and this first condition deals with the relationship between the function itself and its derivative at the left endpoint of our interval that we're interested in. And then the second condition deals with the right endpoint. It deals with the relationship between the function and its derivative at that right endpoint. Now, so this third condition here, it says that K1 and K2 are not both 0, or kappa 1 and kappa 2 are not both 0, and kappa sub 3 and kappa sub 4 are not both 0. All that's saying is that, that I actually have a condition here. If kappa 1 and kappa 2 are both 0, I get 0 equals 0. Doesn't tell me much about the solution of this differential equation. Like, I actually have to have a condition there. And the same is true from that. So as long as these two functions are continuous, and this function p is continuously differentiable so that you can take this derivative and everything makes sense. And we also want that function to be positive, and we want sigma to be positive on the interval that we're interested in. As long as all of that's true, then this is what's called a regular Sturm-Liouville problem, and it's an eigenvalue problem. Now, the rest of what we're going to talk about is really straight from the book. Let's look at example 310. So here's our initial value problem, and this just says, okay, let's say that p is equal to 1, and q is equal to 0, and sigma is equal to 1. Well, in that case, I just have 1 times f prime prime, so that's f double prime, plus 0 times f, which is nothing, plus lambda times 1 times f, so lambda f equals 0. So that's your differential equation. And maybe you're interested in the solution of this differential equation on the interval from a equals 0 to b equals L. So x is between 0 and L. Okay, now let's say that kappa 1 is equal to 1, and kappa 2 is equal to 0, and kappa 3 is equal to 0, and or kappa 3 is equal to 1, and kappa 4 is equal to 0. Well, in that case, if this is 1 and that's 0, and this is 1 and that's 0, That just tells us that f of a, and a is 0, is equal to 0, and f of b, b is L, is equal to 0. That's it. That is a regular Sturm-Liouville problem. Notice it's just a second order differential equation. And again, our goal is to find f and lambda. And we want all the solutions, non-zero solutions, mind you, that will give us f of 0 equal to 0. So when x is 0, the function is 0. And when x is equal to L, the function is 0. It's a very important, very simple, but very important second order differential equation there. Here's another one. This is example 311. All of this is just straight from the book right now. Let's say that all of this is exactly the same. So our differential equation hasn't changed. And the interval is exactly the same. We're just going to change the boundary conditions. So this time, rather than having these as our kappas, we're going to say, let's say kappa 1 is 0 and kappa 2 is 1. Well, that just means we're going to have f prime of our left endpoint equals 0, and our left endpoint is 0. So this is f prime of 0 equals 0. And then we want kappa sub 3 to be equal to 0 and kappa sub 4 to be equal to 1. So we're going to get 0 here, and then 1 times f prime of the left endpoint, that's L, is equal to 0. So that's true. Okay. And that's also a regular Sturm-Liouville problem. And we talk about some applications of differential or partial differential equations. So we talk about the heat equation and the Laplace equation and the wave equation. These conditions will be more meaningful. And so if you're looking for meaning, you're like, what does that mean? Why would I ever solve this? Don't worry, it's coming. But for right now, we're just getting familiar with Sturm-Liouville problems in general. Okay. Now let's say, change the boundary conditions again. Same differential equation. This time though, we want kappa sub 1 to equal 1 and kappa sub 2 to equal 0. So going up here, that's still going to give us 1 times f of 0, or f evaluated at the left endpoint equals 0. And the left endpoint is 0. So this is going to say, or that's going to give us f of 0 equals 0. And then on the other side, we want kappa sub 3 to be equal to h and kappa sub 4 to be equal to 1. So that tells us that h times f evaluated at the left endpoint, or sorry, the right endpoint, left to right, plus f prime evaluated at the right endpoint is equal to 0. So that's an interesting condition as well. We can talk about what that would mean in a particular application problem a bit later. And let's look at another one. So far, we've been sort of sticking with that same differential equation. And we just substituted and we said, okay, if we substitute these values here into the form of a regular Sturm-Liouville problem, we get a particular Sturm-Liouville eigenvalue problem to solve. Sometimes you might look at a problem and wonder, like, is it Sturm-Liouville? So instead of going here and substituting and getting this, you might look at a problem and say, is that one of these? That's like the next problem. So this is example 13.3. Got f double prime plus 2 times f prime plus lambda times f is equal to 0. And we're interested in this particular Sturm-Liouville problem for x between 0 and 1. And we've got f of 0 equals 0 and f of 1 is equal to 0. Now I claim it's a Sturm-Liouville problem, but we have not shown it yet. Let's say someone asks you to show that this is a regular Sturm-Liouville problem It's actually pretty easy to do. Here's the idea. Whoops, where is it? There's my regular Sturm-Liouville problem form. So what I need is a product involving f prime. So I want something times f prime prime. Now, if I take the derivative of that and expand it, I know I'm going to end up with derivative of the first times the second plus the derivative of the second times the first from calculus 1, right? And then you've got a couple of terms over here that just involve f multiplied by functions. One of those functions may not involve lambda at all, but it's given to you. And the other one would involve a function in an extra lambda. So we look at this problem and I see, well, there's my sigma times lambda, or something that will eventually be sigma times lambda, or something like that. But the rest of the problem, this part is not written in this form. So the question might be like, how can I make this sum of two terms look like this? It's actually pretty easy. The idea is the same idea that we used when we solved first order linear differential equations in the ODE class. We want to multiply this. We're going to end up multiplying the whole equation by this function. We're going to multiply by some function so that this is the derivative of a product involving that function. So I said a lot of words. Let's actually write it down. So let's find a function. And that function is typically called an integrating factor. And typically we use the mu. Looks like a U, but it's like a cat. It's a Greek letter mu. I want to find an integrating factor mu so that when I multiply this by mu, I want that these two terms to be the derivative with respect to our independent variable x of this function f prime times the integrating factor. Now that's just another way of writing mu times f prime prime. So you see, multiplying by the integrating factor is a very good idea because we're trying to make this sum of terms involving the first and second derivative of f, we're trying to make it look like this. And if we choose the right function mu, we can make it look like that. Now, we could derive where the formula for mu comes from, but I'm not going to derive it in this video. If you want to know where this formula comes from, you might check out the videos on solving first order linear differential equations. But it turns out that if you let mu equal e to the integral of this power. So you've got nothing multiplying this f double prime except for the mu here. The function that is multiplying that f prime over here, if you let mu be e to that integral power, that will cause this expression to be equal to this expression. So we have mu equals e to the 2x plus c. So that's infinitely many integrating factors. We only need one, so we're going to choose c to be 0. So we'll let mu equal e to the 2x. If I take this, actually, let's just take the whole differential equation and multiply by e to the 2x. So we wanted to find an integrating factor mu such that this is equal to this. And it turns out that mu equals this will work. We get e to the 2x times f double prime plus 2 times e to the 2x times f prime plus lambda times f equals 0. And this is this. It's the derivative with respect to x of e to the 2x times f prime. And if you prefer that prime notation, because that's what we've been looking at, you can say that this is the same as this, e to the 2x times f prime. quantity prime. So if I multiply the differential equation by this integrating factor, I get this. Oops. Don't do that. Make sure you multiply every term in the differential equation by the e to the 2x. Of course, e to the 2x times 0 is just 0. So we end up here. And now let's check it out, make sure that that's satisfied. Calc 1 style. Have the first times the derivative of the second, that's right there, plus the second times the derivative of the first. Derivative of e to the 2x is e to the 2x times the derivative of the inside, which is a 2. So just using the product rule, recall the derivative of a product is derivative of the first times the second plus the derivative of the second times the first. You may have learned that in the reverse order. That's totally fine because addition is commutative. Yeah, this is equal to that. So our original differential equation, which was right here, is actually equivalent to this differential equation. And that is a regular Sturm-Liouville eigenvalue problem. It looks like this. So P is equal to e to the 2x. There's no Q, so that's 0. And it looks like sigma turns out to be e to the 2x as well. So that's our differential equation, and that means we have a regular Sturm-Liouville problem. If you're saying to yourself, look, what's so special about a regular Sturm-Liouville problem? I'll tell you in just a moment. Okay. Here it is. Here's why we care. It's theorem 3.14. This operator that we've been applying to f is one where we take f, we take its derivative, we multiply by p, and then we differentiate, and then we add q times f. That operator, which again is just an operator, a linear operator applied to f on the left-hand side of this differential equation for this regular Sturm-Liouville eigenvalue problem. That operator is, let's say, let me make sure I state all the right things. This operator defined by the left-hand side, I'm going to use the abbreviation LHS. Of our equation 3.2, and acting on a space chi of functions satisfying the boundary conditions. So kappa sub 1 times f of a plus kappa sub 2 times f prime of a equals 0. Something very similar, but evaluated at the left endpoint, kappa sub 3 and kappa sub 4 being our coefficients, equals 0. This operator on the left-hand side of our equation acting on a space chi of functions that satisfies those boundary conditions. That operator is symmetric on x. I keep saying x on chi. Actually looked up the pronunciation for this because I'm always a little bit iffy on the pronunciation of the Greek alphabet. Got to be careful about that. But, you know, mathematicians in the US and anybody studying math in the US tends to pronounce those Greek letters a little differently than they actually do in Greece. I believe I just saw online that it was supposed to be pronounced ki, but we pronounce it chi. You can say the Oklahoma version of our Greek letter chi there. I was a chi omega at the University of Tulsa. We can try to be more like people in Greece. If you're Greek and you're watching this, you can please correct me. I'm Greek, but not in that sense at all. Okay. Here we go. About this operator, it's symmetric on chi. And remember what's special about symmetric operators. We're almost coming full circle here. This is what it means for an operator to be symmetric. You take the operator, apply it to one function, you multiply by the other function, you subtract the other function times the operator applied to the other function. I know I said other a couple of times, but you know what I mean. So this is what it means to be symmetric, but like, why do we care? Why do we care? Because of this. If the operator L in our eigenvalue problem is symmetric, then all of the eigenvalues are real. They form an infinite sequence, and those eigenvalues go to infinity as n goes to infinity. And we get eigenfunctions associated with those. Remember, eigenfunctions are non-zero solutions to that differential equation. So we have infinitely many eigenvalues associated with infinitely many functions. And it turns out later, we're going to see those are the building blocks of other functions, which makes some mathematics really nice. I think you'll enjoy that later. So yeah, so there we are. All of that is to say, when we're talking about a regular Sturm-Liouville problem, the operator is symmetric, and therefore we're guaranteed infinitely many eigenvalues and corresponding to infinitely many eigenfunctions. And those eigenfunctions will be building blocks for other functions later, which is pretty cool. Now, we can prove that this is symmetric. I don't really know. I'm not going to prove that it's symmetric. It's actually it's a very simple proof just using integration by parts. So I'm just going to let you take a look at that if you want to. It's on page 30 of Dr. Constanta's textbook. He just does one case where kappa 1 is not equal to 0 and kappa sub 4 is not equal to 0. Sorry, it's a little blurry. But then you can also look at all the other possible cases for all the other combinations. Remember, kappa 1 and kappa 2 can't be 0 at the same time. Kappa 3 and kappa 4 can't be 0 at the same time. But he goes through this case, this particular case, and says, okay, if I actually put that operator L in there, and this is just the definition of what it means for something to be symmetric. If this is equal to 0 for all f1, f2 in a particular space of functions, then we're talking. Then we know that L is defined to be symmetric. That's what it means to be symmetric. If L satisfies this set equal to 0. If you do this and you do the integration by parts for this term and this term, the ones that involve the derivatives, those are that expression there is what you're going to use for your dv, so that you can take the antiderivative really easily. The antiderivative of a derivative is just the original function. You'll be able to do the integration by parts. And then after doing the integration by parts and substituting the initial conditions and substituting, not initial conditions, boundary conditions, the facts about f of a and f prime of b that come from choosing kappa 1 and kappa 4 to be non-zero. After substituting all of that, you're going to get 0. If you have had calculus 2, it's a simple exercise, and I'll just let you do that on your own. If you want to see me work through it, I'll be happy to work through it with you. If you're a little rusty on your integration by parts, that might be necessary. But it's actually really simple if you still remember integration by parts and can remember that your dv is going to be the part, that factor that has that prime on it. So Dr. Constanta shows you how to do that right there. And you can show that that's true for the other possible combinations of kappa 1, kappa 2, kappa 3, and kappa 4 as well. Okay. And again, this is what I just said. Corollary 3.15. I've always called it a corollary, but I was corrected in graduate school. It's corollary. So the person who corrected me is a very trustworthy source. So whatever you say, it's true. I bet. He's a very intelligent, prolific man, and I will just go with him on that. It's not corollary, it's corollary. the eigenvalues and eigenfunctions of a regular Sturm-Liouville problem have all of the properties listed in theorem 3.8. And it looks just like any other theorem, any other lemma, just stated very simply. It's in italic, there's a period there. There's no giant exclamation point there. There's no highlighting. There's no one reminding you like how big a deal this is, but it's a big deal. The fact that this is a symmetric operator means that we get all this stuff for free. We know that the eigenvalues are going to form a sequence like this, and the eigenfunctions are going to, we get infinitely many eigenfunctions corresponding to infinitely many eigenvalues. We know that those eigenvalues are real. We know all of those things are true. Why? Why do we know that that's true? Because of this fact that this is a symmetric operator. And you say, how can I prove that it's a symmetric operator? Integration by parts, no big deal. Very, very simple. So that's why this is important. I wish there were like blinking lights here, a big sign, like, this is why this matters. This is why you should care. And if you're still saying, okay, like, why do those properties matter? Again, because we're going to use this eigenfunctions as the building blocks for other functions, and that is pretty cool. Allows us to solve a lot of interesting problems. Many interesting problems in physics that you couldn't possibly solve without that combination of eigenfunctions that we're going to come up with later, which is called an eigenfunction, or when we study the eigenfunction expansion method. Okay, so next time we're going to talk about the Rayleigh quotient. I may be mispronouncing that. I'm sorry if I'm mispronouncing that. I'll do the best I can. We're going to talk about that. But that just gives you a formula for lambda. It's really easy to derive that. We'll do that little derivation next time. But actually in practice, we don't use this to find our eigenvalues. We're going to work from first principles because I want to make sure that whenever you study these problems, you actually know where the solutions come from. I never want you to plug and chug, putting your functions p, q, and sigma into some formula and say, oh, well, the lambdas must be this. That's not particularly insightful. So we're going to start from first principles when we solve these problems. But we will occasionally look at that quotient and talk about what that quotient tells us about the values of lambda for some specific examples of regular Sturm-Liouville problems. I think that's enough for this video. So that's some background. Those are what the problems are, and that's what we're trying to find. Now, again, we have not learned how to solve them yet at all, but we've talked about what they are, how to recognize a regular Sturm-Liouville problem, and exactly what it is we're looking for. We're looking for infinitely many functions corresponding to infinitely many values, and these are just different solutions to the differential equation, and they're really important later. These are just regular ODEs, second order ODEs for the most part, but these little ODEs, or they're all going to be second order ODEs for the regular Sturm-Liouville problems. But the solution of these problems, these infinitely many solutions, these families of eigenfunctions, they're really powerful because of what we'll do with them later when we study separation of variables and eigenfunction expansion. So that's it for tonight. Stay tuned. See you next time.